Okay, this is my favorite part. So if you've been following along in the video series, we've been talking about electron configurations and orbital diagrams. And in the last video in part 2, we talked a little bit about how we could relate the Bohr model of the atom to electron configurations. And we just got into talking about the different blocks on the periodic table. So we have the S, the D, the P, and the F block. And I want to talk in this video about how to use those to find the electron configurations, and then also how to find the valence electrons based on their position. And again, the valence electrons are those highest energy, outermost shell electrons that are involved in all the cool chemistry. All right, so let's talk about using the periodic table to find these electron configurations. Now I've redone my sketch of the periodic table, but this time I've included information on the period numbers, right? So if we look at the period numbers on my very wrinkly periodic table here, then we have 7 periods, so 7 rows. We have 18 columns across. If I correspond these 7 periods to these 7 here in my S block, then that's what I'm looking at here. So as I go across in period 4, that goes all the way across, I'm going to travel through my S block into my D block. And this D block starts here with scandium and then goes all the way over. And then as I'm traveling through my D block, I get through to zinc, and then I hop into the P block here with gallium, and then go through to krypton. So that's kind of what I'm showing here with this sketch of the periodic table. So here's my S block, here's my D block for where the d orbitals are, the P block and the F block. Now recall that the intertransition metals actually fit in right here. So they would fit in after rows 6 and 7. It would go directly from 6 and 7 into kind of row 4 and row 5 here of my F block. And then it would go into 5D, 6P, etc. So if we relate this back to our Aufbau principle, then we have the 1s, which gets us through the first 2. Kind of depending on the periodic table that you use, this can be done in a couple different ways. The first row is hydrogen and helium. Helium isn't in the alkali metals though, right? It's not an alkaline earth metal. Oftentimes helium will be stuck up here. And then hydrogen is here. So kind of however you want to reflect that or have that in your head. These are in the same row. These are the only 2 elements in that row. And then with the Aufbau principle here, we go through the 1s, and that's it. We go into the 2s, that gets me through these guys. We go into the 2p, which gets me through to this first row here, which again, if we are relating back to the periodic table, then the 2s would be lithium and beryllium. The 2p gets us from boron to neon. Then if we're going to the 3s, that's next in line, that gets us through here. And then we go to 3p, which would be this row here. So again, if we're going back to our periodic table, 3s goes from sodium to magnesium, 3p from aluminum to argon here at the end. So the Aufbau principle is actually giving us information about how to move through the periodic table to use its position, the element's position on the periodic table, to give us information about its electrons. So it's that powerful. How cool is that? And if you can remember that the numbers correspond in this way, the period number, which is our 1 through 7 down here, the number of the actual row, is going to be true for both the S and the P. So the period number for both S and P is going to follow the actual row number. For the D block, it's going to be 1 less than the row that it's in. So we're in period 4 here, which starts with potassium. But when I hop over to the D block, this is the start of my 3D orbitals, electrons in my 3D orbitals. 3D here. So we're going to start counting down the 3, 4, 5, 6 in the D block, which is 1 fewer than the period number that it's in. Now if we go to the F block, it's going to be 2 fewer than the period it's in, because the 4 Fs start in the 6th period, the 5 Fs start in the 7th period. And this is a lot of talk and perhaps a little bit confusing without actually seeing some examples. So let's actually do some examples. So I'm going to push up my model here just a smidge, and let's look at oxygen. So if we take oxygen on the periodic table, it is element number 8. It is in column 16 or 6A. And so it has 8 protons in its nucleus. That's the information that we get from that. So in a neutral atom, I have the same number of plus signs as minus signs. So I also have 8 valence, or 8 electrons, not 8 valence electrons. We'll get into valence electrons later. We have 8 electrons total. So if I'm figuring out my position on the periodic table, kind of with this schematic in mind, then I have to get through my first row, which the way that this periodic table is hydrogen is kind of floating off in the ether here. And it's partially because it belongs electron-wise in the first column, but it's not itself an alkali metal, right? Hydrogen is a non-metal. So it actually fits more on this side of the periodic table with the other non-metals. But electron-wise, it fits in over here. But so hydrogen is kind of a weird one. Hydrogen is often an exception to things. So this particular periodic table just shows that by putting it out in the ether. So here's row 1, period 1. It contains hydrogen and helium. That gets me through my 1s2. So if I go into oxygen, 1s2 gets me through that first row. Now if I go to the second period, I have lithium and beryllium. This is my S block, and it's in the second row. So to get through to beryllium, because I'm going to count over to oxygen here, right? So I haven't gotten there yet. Then I have to go 2s2. So I have electrons in the first 2 elements are reflected by that. If I count over through the S block here, I have 2s2. Now I'm hopping over to the 2 for my period, P for my block, and I'm going to count over 1, 2, 3, 4 elements, 2, P, 4, and that's my electron configuration, right? So I count up my 2, 4, 8, that gives me 8 electrons, that gives me my oxygen. Pretty cool, right? Let's go down further. Let's do zirconium, because we're feeling frisky. Zirconium. You've probably heard of zirconium before, especially if you've heard of cubic zirconium, which is one way that the zirconium crystallizes. So in cubic zirconium, it kind of looks a little bit like another famous metal. All right, so zirconium's right here, Zr. It's number 40 on the periodic table, so that means it has 40 protons. In a neutral atom of zirconium, I also will have 40 electrons that I'm going to have to account for. All right, so this is going to get long, right? This is my electron configuration for 8. I have to account for 40 of them, so that's a lot. So let's start at the top. We have to go through that first period. To get to helium, I have to get through 1s2. That gets me through that whole first row. Now if I go over to my S block, I need to get through these guys, so that gives me 2s2. I'm still counting down because my target is here, so I need to count all the way through the periodic table to get to that target element. That's the goal. So now I have to get through my P block. I'm in the second period, so that gives me 2p, and then to get all the way through, I need 6. 1, 2, 3, 4, 5, 6. Now I go to the third period through the S block, 3s2. That counts me over to magnesium here. I'm going to hop over to aluminum in the P block to get from aluminum through argon. That's in the third period, the P block. There's 6 elements across. And now I go down to the fourth period. So I'm going through potassium and calcium here. That's my 4s2. And now we get a little bit tricksy because remember our D block starts with the 3 Ds, and we remember that from the Aufbau principle too. That was kind of a weird one. Why does the 3 come after? It has to do with those shifty d orbitals. Shifty. All right, so here's scandium through zinc. If we count over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that makes sense because there's 5 d orbitals and I can put 2 electrons in each of them. I should be able to have a full d block here, a full d line, if I have 10 electrons. So 3, d, 10. I'm through zinc. And if I count up my progress, then I have 2, 4, 10, 12, 18, 20, 30. Oh, almost there. All right, so here's my, I'm trying to get to 40. So here's my next. I'm in gallium. Gallium to krypton. So we're in the 4th period, which for the S and P's matters because that gives me the principal quantum number. So 4p all the way across. To have all of them is 6. Now I'm going to hop down to the 5th period, rubidium and strontium. So 5. I'm going through the S block. 5, S, 2. And then now I'm actually in the row where zirconium is, right? Zirconium is in the 5th period. The D block starts with 3D, so 3D, 4D, 5D, 6D. So when I start here with yttrium, I'm in the 4D orbitals. So I need to count over 4D, 1, 2. So here is my electron configuration for zirconium. If I add up my superscripts, 2, 4, 10, 12, 18, 20, 30, 36, 38, 40 electrons, which accounts for my zirconium. Cool. Now that is just 40. We have 118 elements on the periodic table. That means I could have an electron configuration that accounts for 118 electrons. That would be a lot, and it would take up a lot of space. So there has to be an easier way for us to abbreviate this down a little bit. So the way that we abbreviate this down is by using what we know and love about the noble gases. So you'll see this a couple different ways. Sometimes you'll see it as the abbreviated configuration. Sometimes you'll see it as the noble gas configuration. I kind of like the noble gas configuration because it's a nod to what it really is doing. And the noble gas configuration takes the electron configuration and it stops it at the everything that comes from the noble gas prior to. So I can account for zirconium anyway. Zirconium's here on the periodic table. If I count backwards to my noble gas, so I'm at zirconium 39, 38, 37. If I get to 36, which is krypton, then I can account for the first 36 electrons with just the symbol for krypton, right? If we're just going to use the noble gases to be our benchmark, then if I put krypton in brackets like this, and then I put everything else that comes next, then that's my noble gas configuration. So how much does the krypton account for? Well, we said that it's element number 36 on the periodic table. So it has to account through everything through that 4p6 amount. So that's going to account for all of this. So all of that became this guy. So now what I'm listing out is just what's left over, just what was in the row that came after it, the 5s2, 4d2. And this is also zirconium. This is just called the noble gas or abbreviated configuration. So you're always going to count back to the noble gas and then tell me what's left over. These electrons that are left over are going to be your valence electrons. Those are your highest energy electrons, and kind of depending on where you are in the periodic table, that's going to give you information about kind of the type of chemistry that it can do. It actually impacts the different types of matter.